In today's video, let us learn part 1.3 of chapter 1, which is real numbers and their decimal expansions. In this part, we will start with learning how to find decimal expansions when the numbers are given in the fraction form, and we will also learn how to express these decimal expansions back into p by q or fraction form, and finally we will learn how to find irrational numbers between two different numbers. Let us start with trying to find decimal expansions for the following fractions. The first fraction is 3.2. We can find this decimal expansion by doing long division. So we start doing long division of 3 by 2. So 2 ones are 2 and 1. So we take a decimal here, and which gives us a 0 here, so 5, and 2 5s are 10, and we are left with nothing. So we got the answer as 1.5. Let's move on to the second fraction and try to find a similar decimal expansion for this one. So 3 goes here, 1 goes here. So 1 is smaller than 3. We have to start with a decimal. 3 3s are 9, and I get 1 again, but because we had a decimal there's a 0, so 3 3s are 9 again. We can see what's happening here is that this is recurring, 3 is recurring. So the moment we end up with what we started, we can understand that the decimal is going to recur. So the answer for 1.3 is a recurring decimal, which we can write in this form, which also can be written as 0.3 bar. We put this bar on the recurring part of the decimal expansion. Let's look at the third one. So 10 by 7, 7 and 10. 7 ones are 7. What are we left with? 3. So 3 is smaller than 7. Let's take a decimal. 7 4s, 28. 2, 7 2s, 14, so 6, and 7 8s, 56, 4, 7 5s, 35, 5, 7 7s, 49, 1. So we go back again, and 7 ones, 7, 3. So you can see what's happening is at this particular point we have started getting a recurring decimal, because you can see that is where we started. So this whole thing is going to recur. So we can write 10 by 7 as 1.42857 bar, that is this 42857 is going to recur continuously. So in these decimal expansions, we can see two types of numbers that we are getting as solutions. The first one is non-recurring, and it also terminates, that is, it is terminating and non-recurring. So this combination we call as rational. 1 by 3 similarly is recurring and non-terminating. So this is also rational. Similarly, 10 by 7 is also a recurring and a non-terminating decimal, which is also rational. So by looking at these different types of decimal expansions, we can see that either it can be recurring or non-recurring, and terminating or non-terminating. The terminating number can be a single number or multiple numbers. That's what we understand by looking at these different decimal expansions. Now let's look at how we can show these recurring decimals in terms of fractions. So we saw how fractions can be expressed in terms of decimals. Now we learn how to do the opposite. In this question, we see how to represent 0.3 in p by q form, for example, where 3 is the recurring decimal. Now the first step is to let x equals to 0.3 bar or 0.333 so on as equation 1. The second step is we multiply equation 1 with 10 on both sides. So we see the number of decimals that are recurring and we take that many zeros. Because we have only one decimal that's recurring, we are multiplying with 10 on both sides. So when we multiply with 10 on both sides, that is 10 into x and equals to 10 into 0.3 bar is going to result in 10x equals to, so upon multiplying with 10, the decimal will be moving by 1 point and 3 will move to this side. However, 3 will still be recurring. So 3.333 so on. Now we have equation 1 and equation 2. The next step is to subtract equation 1 from equation 2 so that we can get rid of this recurring part. Let's see how to do that. Equation 2 minus equation 1 can be done in this way, where 10x minus x will give us 9x and 3.3 bar minus 0.3 bar will be left with 3. So x can be written as 3 by 9, which is nothing but 1 by 3. That's how we convert our recurring decimal back to a fraction. Now let us take a look at another example where we can represent 0.235 bar in P by Q form, where you can see that not the whole decimal is recurring but just the 3/5 after the 2 is recurring. Let's see how to convert these kind of decimals back into fractions. First step is similar to the last method, where we let x equals to the given decimal. We take that as equation 1. And the second step is to multiply equation 1 with 10, because in this we have two steps, where in the first step we get the number that is not recurring in front of the decimal point. So we multiply it with 10. So 10x is going to give me 2.3535 so on, which will be equation 2. Now what we are going to do is bring the recurring decimal also outside the decimal point. How can we do that? How many are repeating here or recurring? 3, 5, 2 numbers are recurring. So we multiply with 100. Let's multiply equation 2 with 100. We get 10x into 100 equals to 100 into 2.353535 so on. So 10 into 100 is 1000x and 100 into 2.35 so on is, we get two decimals out after multiplying with 100, that is 235.3535 so on, and this will be our equation 3. Now remember, in order to bring to P by Q form, we have to remove the recurring part. How can we do that? Equation 3 minus equation 2 will get rid of that part. As you can see here, subtracting equation 3 minus equation 2 will give us 1000x minus 10x, which is 990x, and 235.3535 so on minus 2.3535 so on will result in this 3535 and this one get cancelled, and we are left with 233. So 990x is 233, and if I send the 990 on the other side, left with a fraction 233 by 990. So that's how we have converted this decimal into this fraction over here. Let's move on to the next part, which is finding irrational numbers between two numbers. In our previous video, we learned how to find rational numbers between two numbers. Now let us see how to find irrational numbers. First example, we have two numbers 5 and 6. How to find irrational numbers between these two numbers? So the first step is you have to find square root of 5 and 6, which is square root 30. This is an irrational number, right? So how do we know this is an irrational number? This is not a perfect square. Every number that is not a perfect square in the list of integers that are perfect squares is an irrational number. So for example, under root 30 is an irrational number. How do I know that? I take a look at the list of perfect squares here. I can see that after 25 I get 36. So 30 here is an irrational number, where 25 and 36 are rational. So as a part of CBSE, you have to remember at least 20 perfect squares in order to do these kind of exercise questions. Now, how do we find more of these irrational numbers? So as we saw in the list of rational numbers, perfect square of 5 is 25. Perfect square of 6 is square root 36. Anything between these two is an irrational number. So I can think of some irrational numbers between these two, for example, root 26, 27, 28, 29. So all of these and 30, for example, are 5 irrational numbers between 5 and 6. We can find 5 more irrational numbers from root 30 to root 36 as well. Now let us see how to find irrational numbers between two fractions. The first step is to expand these fractions into decimals. We have expanded 1 by 7 earlier, so that is, it looks something like this. Once you expand 1 by 7, you get the fraction into decimal as 0.142857 bar. Now 2 by 7 can be found easily without expanding again in using long division. How can we do that? We can say 2 by 7 is 2 into 1 by 7, and we get this value over here, which is 0.285714 bar, which is the decimal expansion of 1 by 7 and 2 by 7. Now we know that these are the two decimal expansions. What is an irrational number? An irrational number is the one that is non-terminating and non-recurring. So you can see here we have 0.14 and 0.28. We can imagine that there can be infinite irrational numbers between these two numbers, and we can write those. The irrational numbers can be written as 0.15, 0213, so on, 0.1638, 00102, so on. So the only criteria that we have to fulfill is that they are non-recurring and non-terminating, and that they are in between these two. In that way we can write infinite irrational numbers between these two numbers. Now that we have learnt how to write decimal expansions and convert them into P by Q form and also find irrational numbers between two numbers, let's move on to exercise 1.3. The first question asks us to find decimal expansions and say what kind of decimal expansion each has. So let's start with the first one, which is 36 by 100. When I do the long division of 36 by 100, I get 0.36. This kind of a decimal, what is this? It is a terminating and non-recurring. So we can call it as a terminating decimal. Now let's look at another question, 1 by 11, and see what kind of a decimal expansion this has. When I divide 1 by 11, I am starting with 1. So I need 2 more zeros in order to divide with 11. So I take 0.0 here, and 11 nines are 99. I am left with 1. Because of the decimal I get a 0, but I need to add another 0 because 10 is still smaller than 11. So again I have to do 11 nines are 99, and I am left with 10 again, and I would have to go for another 0 if I had to continue the long division. So what we can observe here is that this is a non-terminating decimal and it is also recurring, and the recurring part here is 09. So 0.09, where we put the bar on 09, and this is a non-terminating and recurring decimal. The third question is 4 1 by 8. This is a mixed fraction. Before we find the decimal expansion for the mixed fraction, let us convert it into a proper fraction, and we can do this by multiplying 8 into 4 plus 1 by 8, and we get 33 by 8. This is the proper fraction, and now we can go ahead with long division to find the decimal expansion. So I start with 33 and 8, 8 4s are 32, and I am left with 1. So I take a decimal point here, and 8 1s are 8, and I am left with 20, and 8 2s are 16, I am left with 4, and 8 5s are 40, and I am left with 0. So this is a terminating decimal, and the answer is 4.125. Let's take a look at the next question, 3 by 13. So when I am doing the long division of 3 by 13, I can see that I am coming back to where I started, that is this 30 is coming here. So I know that this part is going to be the recurring part. So my answer is 0.230769 bar, which is a non-terminating and a recurring decimal. The next one is 2 by 11. Starting with the division of 11 with 2, I have to take a decimal, and when I start doing this long division, I can see that again this 20 has come back. That means this 18 is going to recur, and my answer is 0.18 bar, which is non-terminating and a recurring decimal. Next fraction that is given to us is 329 by 400. Let's see how to do this. So a simple way in order to divide with a smaller number is to separate this 100 and we can divide by it later. So 329 by 4 into 1 by 100, I can write it this way. Now let us first expand 329 by 4. Once I have expanded 329 by 4, I have got my answer as 82.85. Now in order to find this, I have to divide further by 100. We know that when we divide by 100, the decimal moves by 2 points forward, which will give me 0.8225, which is still a terminating decimal. Second question tells us we know 1.7 is 0.142857 bar, and it asks us to predict 2 by 7, 3 by 7, 4 by 7, 5 by 7 and 6 by 7. Let's see how to do this. So 1 by 7 is the value given to us. Let's see how we can find 2 by 7. So we can say 2 by 7 is 2 into 1 by 7. So I can multiply this decimal with 2, and you can see the multiplication that I have done here. So the multiplication has resulted in 0.285714. So I can say 2 by 7 is 0.285714 bar. Similarly, I can find the value of 3 by 7, which is 3 into 1 by 7. Upon multiplying, I get this value over here, and similarly I can find the value of 4 by 7, 5 by 7 and 6 by 7. So once we have one decimal, this is how we can predict the multiples of that decimal. The third question asks us to express recurring decimals in P by Q form, where P and Q are integers and Q is not equal to 0. First decimal given to us is 0.6 bar, where 6 is the recurring decimal. So we know that we have to start with assumption that x equals to the given decimal, which is 0.666 so on. Because we have one number that is recurring, we multiply the equation with 10 on both sides, which results in 10x equals to 6.666 so on. Let us say this is equation 2. In order to eliminate this recurring decimal, I have to do equation 2 minus equation 1, which gives me 10x minus x is equal to 9x, and 6.6 bar minus 0.6 bar equals to 6. Now this can be further simplified as x equals to 6 by 9, that becomes 2 by 3 because 3 2s are 6 and 3 3s are 9. We know from equation 1 that x equals to 0.6 bar. So now I can say that x equals to 2 by 3, which is equal to 0.6 bar. That is how we have converted our recurring decimal into a fraction. Second question is a decimal 0.47 bar. Here you can see only 7 is recurring, 4 is not. So let us start this problem by assuming x equals to 0.477 so on. The first step should be bringing this number that is not recurring outside the decimal. How can we do that? Multiply equation 1 with 10. Upon multiplying, I end up with 10x equals to 4.777 so on. The next step is now to ensure that we multiply with the number of zeros that is equal to the number of recurring decimals, which is 10, because one number is recurring. 10x into 10x will give me 100x, and this 7 will come outside, so that will make it 47.777 so on, which is equation 3. Now we have to do equation 3 minus equation 2 in order to eliminate the recurring decimal, which will give me 100x minus 10x is 90x equals to 43. So x will be 43 by 90. So from equation 1, I can say that 0.47 bar equals to 43 by 90. Fourth question asks us to express 0.9 bar in P by Q form and discuss our answer. So let us follow the step-by-step process that we were using. We assume x is 0.9 bar. Because one number is repeating, we multiply with 10 and we get 10x equals to 9.999 so on. And now we subtract equation 2 minus equation 1, and what do I end up with? 10x minus 9x is 9, and these two parts get eliminated. 9 minus 0 is 9. So x equals to 9 by 9, which equals to 1. So this is interesting. In this case, we haven't ended up with a fraction like earlier, but we ended up with a whole number. That is the difference between other decimals that we have converted into fractions, and this one. Fifth question asks us to find what are the maximum number of repeating digits in 1 by 17 expansion. Let us start with the long division of 1 by 17. So starting with 17 and 1, I took a decimal and added another 0 in order to get 100, because 17 is greater than both 1 and 10. Now performing the long division has given me all these numbers, so you can see the process of long division over here. Now you can see how I come back to 1, that is where I started. So after all these number of digits. Now in order to answer this particular question, what are the maximum number of digits? Now I have to count these digits: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the number of repeating digits is 16. That's the answer to this question. Question 6 of exercise 1.3 asks us to look at examples of rational numbers in P by Q form, where P and Q are integers with no common factors other than 1 and have terminating decimals. What property must Q satisfy? So let's look at this point where they say P and Q are integers with no common factors. That means P and Q are prime numbers. A prime number is the number that has a factor of 1 and itself. So similarly, we can find some integers that have no common factors other than 1 and see the P by Q form. In order to write in P by Q form, the number has to be rational and terminating, and the condition given is only 1 and itself as factors. So starting with 2 by 2, 2 is a prime number and we get 1. Okay, this is in P by Q form and I have a terminating decimal. Next 2 by 3, if I want to do, this is in P by Q form, but it is a non-terminating decimal. So looking at some other examples, 2 by 5, 0.4, and some more examples that I have over here, 3 by 5, 0.6. So all the terminating decimals I have marked as correct, and all the non-terminating or recurring decimals I have marked as cross. So what can we see for the value of Q as common, where we are getting a terminating decimal? So this 2, 3 and 5 and 7, all these are prime numbers that we are satisfying, and we can notice something, that when we are getting P by Q as a terminating decimal is when Q is either 2 or 5. So the answer is Q should be either 2 or 5. Seventh question, write 3 numbers whose decimal expansions are non-terminating and non-recurring. So non-terminating and non-recurring is nothing but irrational numbers. How do we know what are the irrational numbers? The numbers that don't have perfect squares, like we discussed earlier. So for example, we know root 2, which is 1.414213. We know that this is an irrational number. The second example can be root 3. This also doesn't have a perfect square, and root 3 gives us the value of 1.7320508, etc. And another famous non-terminating, non-recurring number, which is an irrational number, is pi. Pi is 3.14159265, so on. So these can be 3 examples of the decimal expansions which are non-terminating and non-recurring. Eighth question asks us to find different irrational numbers between 5 by 7 and 9 by 11. So we have to find 3 different irrational numbers. Let's start with the decimal expansion of 5 by 7. So the decimal expansion of 5 by 7 gives us 0.714287, where 14582857 is the recurring one, and the decimal expansion of 9 by 11 gives us 0.81. So now we have 0.71 and 0.81 as recurring decimals over here. In order to find irrational numbers, I can write the numbers that fall between these two. So the 3 irrational numbers can be 0.72, so on, 0.73, so on, 0.74, so on. So that is how I can imagine, or I can find irrational numbers that can lie between these two numbers. The 9th question asks us to classify as rational or irrational. Let's look at the first number. The first number is under root 23. So we know square root of 23 is not a perfect square. So it is irrational and it cannot be written in the p by q form. Let's look at the second number. It is square root 225. Now let's take a look at our perfect squares. So we have square root of 225 over here, which is 15. So the answer for square root of 225 is 15, which shows that it is rational number and it is a perfect square. Let us take a look at the third number. The third number is 0.3796. Now we can see that this is a decimal number, but we can say that it is rational because it is a terminating decimal. Fourth one is 0.478478, so on, where we can see this 478 is recurring. So this is also a rational number because we have a non-terminating and a recurring decimal. Let's take a look at the fifth question. Fifth question says 1.101001001, so on. We do not see a recurring pattern over here, and this is a non-terminating decimal. So this is irrational because it is non-terminating and non-recurring. With this, we have reached the end of 1.3.